So, maybe a little unexpectedly, a lot of our understanding of atomic structure and behavior and properties actually depends on our understanding of how light works, and more specifically, any type of electromagnetic radiation. So that can include visible light that helps you see, or it can include things like radio waves or X-rays, or lots of different types of radiation. And electromagnetic radiation carries energy through space. And light of any type can generally be treated by the kind of high school wave physics that you may have encountered. So, very brief review of wave physics. Electromagnetic radiation can have a wavelength and a frequency. So assume you have some electromagnetic radiation and it's traveling from left to right across the screen. So this radiation is going to have a wave characteristic, so you've got repeating structures where you have peaks and troughs. And the gap between any two peaks or any two troughs is what's known as the wavelength of light. So the wavelength is the distance between any peaks or troughs, and it's measured in meters. It's actually a physical separation between these peaks and troughs. And the other property of radiation that we typically measure is frequency, which is the number of complete wavelengths that go through a point every second. And frequency is measured in seconds to the -1, so per second, or you can also use the unit of hertz, which is the same thing. And from the wavelength and the frequency of light, we can work out the speed of light. Speed is typically measured in meters per second, and we have units that give you meters, and we have units that give you per second. So we can use wavelength times frequency to give us speed of light. And the interesting thing about electromagnetic radiation is that the speed of all electromagnetic radiation is the same. Doesn't matter if it's visible light or if it's infrared or radio waves, the speed of that electromagnetic radiation is always going to be the same. And that's very close to 3 times 10 to the 8 meters per second. And a little bit of a caveat here, this speed of light is only true in a vacuum. If the light is moving through air or water or whatever, it varies a little bit. And the nice thing is, because this speed of light is a constant, we can see that the wavelength and frequency have to be inversely proportional to one another. That is, as the wavelength goes up, the frequency goes down, and vice versa. We can also rewrite this in terms of an equation, and we would write that as C equals lambda nu. So C is simply the speed of light, and the Greek letter lambda is our wavelength. And the Greek letter nu is our frequency. So I've rewritten the expression now. You can see that because the speed of light is a constant, lambda and nu are inversely proportional to one another. And if you look at the image on the right-hand side of the screen, this is a representation of the electromagnetic spectrum. If you look at the top, you can see that wavelength is increasing from left to right. And at the bottom part, you can see that the frequency is increasing from right to left. So if you look at something like radio frequencies, you can see that when you have a fairly large wavelength, so radio frequencies can be up to 1,000 meters, a whole kilometer, you'll see a fairly low frequency. Right, so 10 to the 3 meters for the wavelength and 10 to the 5 hertz, 10 to the 5 seconds to the -1 for the frequency. But if you drop down into the X-ray spectrum, you can see that as the wavelength gets smaller, now 10 to the -9 meters, you can see that the frequency gets enormously larger, right? So 10 to the 17, 10 to the 18 hertz. The other thing that's highlighted by this image is the fact that the visible region of the spectrum is very small. So the visible spectrum is only a very, very small part of the entire electromagnetic spectrum. And the blown up version, which runs from 400 to 750, is not actually in meters, it's in terms of nanometers.